In this series of pages, we're actually going to get to the calculus of the integral for those who have seen it before. So we talked about taking a sum of f of xi's, and we added that little star to capture the generic sum point on an interval. And what that gave us was a bunch of rectangles that represented an estimate or an approximation to the area underneath some curve. And that's what we're really interested in, is the area under the curve. Well, as you draw these pictures over some time, you recognize quickly that the narrower the rectangles, the more accurate your estimate's going to be. And so that leads us to the idea of, well, instead of using 6 or 12 or 10 or 100 or 1,000 rectangles, why don't we take a limit and let's take the number of rectangles and let it approach infinity. Another way to say that is let the interval width approach 0. We can see in this formula that the width of each rectangle, of course, gets smaller as we use more and more rectangles on the same a to b interval overall. And we can see why we need to use a limit in this, because of course we have function values times something. We can't just use 0 as our width. We have to approach 0 and see how that works out. Now this limit is called the definite integral of f of x from a to b, and it's equal to the area under the curve. So this is the exact area under a curved region because we're using the limit as we use more and more rectangles or smaller and smaller rectangles, which gets more and more accurate. Now, this, I think we'll all agree, is a lot to write out if we wanted to find that area. We should still see again that pattern of height times width in it. But we're going to convert it to a similar notation. So I want you to take a look at this here first. Look at the pieces, a sum, function values, and delta x's, and we'll compare it to what we get when we convert it to the traditional integral notation. This summation notation here is actually a capital S. So this is a script S. It's meant to capture that idea of the sum of xi's, stars, delta x's, I equals 1 to n. So when we take the limit, as n goes to infinity, of this series, of this sum here, we get this integral. So this is the concept, this is the execution. So when we write in this simple notation, integral from x equals a, it's important to remind ourselves that these a and b values are x values. The integral from x equals a to b of f of x dx, that is the area under the curve, that is the limit of rectangles with heights times widths. And you can see the parallels. We've got the heights, f of x. Before we had specific heights, now it's just all the heights all the way between a and b. Instead of delta x, we have, dx, our familiar friend from derivatives. We took limits of delta x going to 0. And instead of the sum, we're going to have this integral sign. So this was not an arbitrary choice of notation by any means. It was meant to mimic the kinds of things that we saw when we were finding areas with a brute force approach. Finally, getting back to some connection to the kinds of problems we'd ask in class, how would we write the definite integral that represents the area underneath the graph of our function between x equals 2, that's x equals a, and x equals 4, that's our x equals b. So imagine what we're talking about here. We have some graph with a cosine thing happening. We've got x equals 2, we've got x equals 4, and we're going to subdivide that into a large number, an increasing number of intervals. How do we represent that area? Well, that area can be written notation-wise as the integral from 2 to 4 of x plus cos of x dx. And again, think of that as an equivalent to the sum of some function values, which is x sub I plus cos of x sub I, all times delta x, heights times widths. If you keep that structure in mind, then it'll make the integral much easier to write out. The other way we can phrase that now, because we don't really have tools to exactly evaluate this, we just have an idea, what we can do instead is say this area is equal to the area underneath the graph of x squared, of y equals x squared, on the interval from 0 to 2. So 0 to 2 is our interval of interest. And then we could estimate that by using a finite number of rectangles. Of course, this one here, the whole point is it represents the exact area with an infinite number of rectangles, or the limit of that infinite number of rectangles. It's very common to be presented with the exact thing that we would like to calculate and then to approximate it with something else, which we can calculate without limits. So here we're going to take 4 subintervals, and we note what those dividing points would be then, 0.5, 1, and 1.5. We're going to use a right-hand sum. So what we would say here is that the integral from 0 to 2 of x squared dx is going to be approximated by, here I'll write out the gory sum notation to see the parallel again. It'll be the sum from I equals 1 to n usually, but here we've been told we're going to use 4 intervals exactly. The right-hand endpoints have the sum of x sub I. How does that notation work again? We start off with x0, we end at 2 with x4, and then it's 1, 2, 3, x2, x1, x3, x4. When we convert that to more traditional sum notation, just because we want to find the values, we would use the 0.5, 1, 1.5, and 2. So x sub 1 is our first point that we plug into our function. That gives us f of 0.5 times delta x. What's our interval here? Our delta x is 2 for the whole interval, and we're dividing it by n. I'll actually do that in the general case first. 2 minus 0 over 4, which is a half. So we're going to have intervals of 1/2. You can actually see that again on the picture. Don't overcomplicate by memorizing the formulas or being too attached to them. It's easy to see on the diagram what widths we're talking about here. And we keep going. We're going to have f of 1 times 0.5, and we'll need 4 elements in the sum. And the last one would be f of 2 and 0.5. So an important note again, the 0.5s don't change. The 0.5, those are always the same because they're the widths. What does change is the number inside the function value, because that's where we're taking our function height, and that changes as we move from left to right. So widths are constant. The heights are not constant. What does that give us in terms of calculations? Well, we get 0.5 squared plus 1 squared plus 1.5 squared plus 2 squared, and every term had a 0.5, so we'll just multiply that by all the terms at the end as a common factor. When we do this calculation, we get a total of 3.75 square units. So what we've generated here is this rectangular approximation to the area under the curve as an estimate of the exact area denoted by the integral sign. Let's draw that a little more accurately. We were given the integral from 0 to 2, and so the exact area under that graph would be highlighted here. That region is exactly equal to the integral from 0 to 2 of x squared dx, while in contrast, we still stop at 2, we still start at 0, but using right-hand endpoints and only 4 intervals, we get these 4 rectangles, and their area is equal to the left-hand approximation with 4 intervals, and so it's an approximation only to that same integral value. A little bit of an overestimate in this case.